Good morning. What I'd like to introduce to you today is a classic experiment to measure the acceleration of gravity near the surface of the Earth over a very small distance. When an object is dropped near the surface of the Earth and does not fall a significant distance, the acceleration of gravity is constant. And so we'd like to measure that constant value by dropping something near the surface of the Earth. So we're going to use this mass. This mass was selected because it has a steel core and will be attracted to this electromagnet at the top of the Senko acceleration of gravity measuring device. Recall your basic physics that all masses fall at the same rate near the surface of the Earth in a vacuum. The force acting on the mass is of course different. Remember that the force is equal to the weight of the object, the mass times the acceleration of gravity. So the force is larger for larger masses. It grows exactly at such a rate that when you release an object and it falls at 9.81 meters per second squared downwards. In order to describe that, I had to establish a coordinate system, and I picked my y direction to be vertical, the x to be horizontal. This object will fall in a negative y direction, so I say the acceleration in the y direction is equal to negative g, g being the acceleration of gravity, which is a constant. Recall from basic kinematics, if you know the value of g, if I release an object at rest, and initially it'll be at rest at the top of the magnet, then there's no initial velocity in the y direction. The velocity will grow linearly with time. It'll be negative because it's going downwards in this coordinate system and increase at a rate of negative 9.8 meters per second squared times seconds gives meters per second for the y velocity. How does the distance change? Recall from kinematics, the distance changes in a parabolic fashion. I will set my coordinate origin to be at 0 at the top where the electromagnet is. So y0 is 0, v0y, the initial velocity is 0. The acceleration of y is negative 9.8 divided by 2 is negative 4.9 t squared. I turn the power on the electromagnet, and then I take the steel core, I place it right up here, there. So the idea is that if I break the circuit so that there's no power in the magnet, the object will fall. It's attached to a spark generator. This is a high voltage, 20,000 volts, but low current, 2 milliamp device, so that when this releases, it will ground through this piece of paper to the steel pole behind it. Each time it arcs, it will leave a little tiny spark hole in the paper, and so I can then measure those. It's in a 60 hertz outlet, so I get 60 sparks a second, and I know the time, and then I can check to see if these equations are true. Does the velocity increase linearly with time? Does the displacement increase quadratically with time? All I have to do is hit this button. Turn off the magnet. And collect the data. By cutting the paper, the top and the bottom, and then giving it to you to analyze, you can then verify by plotting directly the displacement and velocity as a function of time. You expect to get a line. The slope of that line is going to be the acceleration of gravity. You expect to get a parabola. When you take the tangent of that curve, you expect that to be the velocity. If you take any 2 points, you can get delta v. You can calculate the acceleration of gravity. To a curve fit, to a quadratic equation, the coefficient in front of t squared better be minus 4.9. Collect your data, see what you get. You should be able to verify within 1% the acceleration of gravity near the surface of the Earth, ignoring friction, is about 9.1 meters per second squared in magnitude. Good luck.